We wrote the solution of the potential that P star minus, this is W on the aerofoil, minus mu z for z greater than 0, and then had this for z less than 0. So you see that antisymmetry, but this is the phi star at any location z. But if you want to get the phi, you have to do the inverse Laplace transform. But we are interested in the solution where z equal to 0, because we are not interested in getting the potential at every point. Only on the aerofoil we get the pressure, then we can write the solution. Therefore, we set z equal to 0, and then we will do the 0 plus comma p, which is minus W a star, which is, this is the velocity at the aerofoil, and similarly P star theta minus P, you will have W a star over mu. This is z greater than 0, this is z less than 0. Now this is the product of two Laplace transform, because mu is a function of P. So when you have products of two Laplace transform, then actually this is where the Laplace of, if you have two functions, this is basically f of p, g of p. That means product of two Laplace transform is basically the convolution of the two functions. Convolution is, we will write it like this, g of t, which is integral 0 to t f of tau g t minus tau d tau. Okay. Now we simply apply this solution technique. This. When we apply, we will get phi bar 0 plus comma, which is the function of p becomes x, because p is the Laplace transform for x. This will be minus integral, same thing, 0 to x, because this minus is because of this minus. Okay. And W a star, that will become W bar a, which is a function of some xi, because this x is going to be there, and then Laplace of that inverse of 1 over mu, 1 over this into d xi. Now Laplace inverse of 1 over mu, because if you look at it with, please understand this, I have to have like t minus tau, so I will have x minus xi for this when I write the Laplace. But mu, you go back to your notes and then look at what is the form of the mu which we wrote. If you see that we wrote mu square, I will just write it here so that it is clear. Mu square, we wrote m, we use m infinity or m. So okay, m square minus 1 p plus I m omega over a infinity m square minus 1 whole square plus omega square over a infinity square m square minus 1 whole square. Okay. This is like one square quantity plus another square quantity. Now if we have, that is the mu, Laplace inverse of 1 over square root of p square plus alpha square. Okay. This is actually a Bessel function. Okay. And then if p is added with, because p plus some quantity, that means I am doing a shifting theorem. So if you have a shifting, because Laplace inverse of, you know, f of p plus a is nothing but e power minus a x f of x. Okay. So you use these two to write the solution for this. Now the solution will be, because you know that mu, I will write the expression for 1 over mu. 1 over mu is 1 over m square minus 1 divided by bracket open p plus I m omega over a infinity m square minus 1 whole square plus omega square over a infinity square m square minus 1 whole square power half. So this is my mu. Okay. And we have the Laplace inverse for this. So I'll write my final solution. Maybe I erase here, because this is going to be a long expression. Okay. This will be p bar 0 plus comma x is nothing but minus 1 over m square minus 1 0 to x w bar a xi e to the power minus I m omega over a infinity square, a infinity into m square minus 1. That is this term, that is the shifting. And shift we have to, because this is a convolution, we have to do the convolution for that. Convolution is t minus tau. So this x will become x minus xi into j naught. Maybe I erase this part, because this entire term is exponential, into j0 of omega, because alpha x, alpha is this term. Okay, this is alpha square, half of that, omega over a infinity m square minus 1 into x minus into d. Please understand, this is within the bracket. Okay, I will put it like this. Okay. Oh, sorry, this is a square root. Yeah, I am sorry. This is a square root. Yeah. Okay. Now this is my phi. You can actually calculate this, because we are going to make approximations later. What we are doing is, we will non-dimensionalize this and write it in a compact form. but there is a paper in 19, actually it's a NACA report. They have obtained this, and then it gives a table. I'll write that reference to you. It gives the complete value of these integrals. Okay, because this is the Bessel function, and this is an exponential sum term, and we will non-dimensionalize it by writing the length we non-dimensionalize with respect to card, that is 2b, and we'll put a star. X star is x over 2b. So you see, if I want phi only on the, because phi at any x 0 plus, okay, my integration starts from 0 to x. If I want only over the aerofoil, I'll just integrate this only up to the aerofoil, okay, and this is nothing but the velocity of the fluid at the aerofoil, basically the W velocity. You say the W velocity is nothing but the velocity of the aerofoil itself. So you know this motion, then you can always get this phi. Once you get phi, you can get the pressure expression. So that is how it is done. Now let us write this, and then you define one more, which is omega bar as 2k m square over m square minus 1. Okay. Now what is this k? K is b omega over u infinity. This is a non-dimensional parameter which is called reduced frequency. Okay. This is called reduced frequency. This is important for unsteady aerodynamics. This is nothing but omega, because we have assumed that the aerofoil is oscillating, because if you look back, it is a harmonic motion. If it is having a omega, b over u infinity is the far field velocity, and this is the reduced frequency. Okay. Later we will do approximations based on only this. Very high omega, very low omega, because in between you have to use this expression only. Now your expression in non-dimensional form, it will become, okay, I am writing it here, phi bar of 0 plus comma x star. This is minus 2b over root of m square minus 1 integral 0 to x star w a xi star e power minus I omega bar x star minus xi star j naught omega bar over m x star minus xi. Okay, this is my solution. Okay, now you go back, you have to use the unsteady pressure expression, the pressure difference. Okay, so I'll write the final solution. Okay, the pressure on the upper surface, because this is P minus P infinity, okay, that is what I am putting it as. This is rho infinity delta phi by delta T at This is our pressure expression, P minus P infinity. Now, if my phi, because what we assume, our phi is phi bar e power I omega t. This is what we have assumed. Now, I am going to substitute this here. If I substitute, this will become P bar, because P also we said pressure is also fluctuating. P, this is P hat, maybe I will put it like this. I omega t, I may put a u, because when this is oscillating, pressure is oscillating, everything is a steady oscillation. This will be minus rho infinity I omega phi bar, because e power I omega t I am cancelling out, plus u infinity delta phi bar over delta x at z equals 0 plus P upper, P upper. Now this itself can be non-dimensionalized by writing it minus rho infinity, you take out u infinity outside and you divide by b, this will become I k phi bar plus half right. Now you can also have lower surface. Lower surface you will have just change L, okay, because please note that, okay, this is, I should change it to X star, I am sorry, because star star, please understand the factor 2 comes because it is X over 2b, okay, that is why that star. Now you see, this is the pressure on the upper surface. Similarly, you will have pressure on the lower surface with the same expression, only thing is Z minus. One, you have to subtract the other one, okay. When you subtract this minus of the same quantity, you will get that will become plus. But you know that phi, top surface and the bottom surface, they are antisymmetric. Therefore, your P u minus P L, okay, upper surface minus lower surface, I will write it here, maybe there is a little space, it will become P bar u minus P bar lower surface, this minus 2 rho infinity u infinity over b I k phi bar plus half delta phi bar over delta x star at z equal to 0 plus, okay. So this is my differential pressure, okay. Now if I know the pressure, the phi bar, I know it here, that means only thing is, if I know this integral, please understand this integral is a function of this omega, okay. That means for every omega bar, you will have a value, you understand. That is how the integrals are defined, okay. Later you will learn how to apply, if I have this type, how do I solve my flutter problem, that we will learn later. First we will get only the unsteady aerodynamic load. Now let us take, this is the pressure, that means if I know the pressure, I can get the lift, I can get the moment about any point. So we will write the expression for that, and maybe I erase this entire part now. Okay. So my lift expression, because if I have my aerofoil, please take this. This is my thing. What you will have, you will come down. Let me have it. Because you say this may be your B and this may be your location where it is coming down. This is my H and this angle is alpha. Okay, this is the center of the aerofoil. This is where my springs are attached. If you go back to your old thing, reference. So this is H, this is alpha, and your flow is coming this way. And you define your distance. This is x0. Of course, this is semi-chord. This is also semi-chord B. Okay. And x is along this direction. So you measure x from the leading edge. Please understand our integral. You measure from the leading edge because the phi ahead of the disturbance. Therefore, you always have the integration starts from the leading edge and then you proceed to any x. Okay. So your leading edge always becomes, that is why I put x naught. So you define this is at any x. This is any x. Okay. And of course, this is your z. Write your lift as 2b integral 0 to 1 p bar lower minus p bar upper into dx star. Lower minus upper means I just put a minus sign, minus and minus, that will become plus. So this is my lift, and moment about the elastic axis or the point about which I am measuring the rotation. So my moment on the aerofoil becomes 4b square, again 0 to 1. Now please note I use p bar upper minus p bar lower into x star minus x naught star dx star. Because this is my nose up moment is taken as positive. That's why please note that this is nose up moment. Nose up. Because alpha is taken this way. So P upper minus P lower is the force. That into x minus x naught is this. That is what I am saying. And that moment is in the nose up direction. Okay. Now you find out, see, this expression you have to obtain. First phi, then this phi you have to substitute here. Okay. And then get your lifted moment. Okay. Now, for the sake of this, I will write that okay. This is NACA 846. This is in 1946, please understand. Garrick and Ruby now. Okay. how they have represented is, they wrote my lift as 4 rho infinity u infinity, okay, rho infinity u infinity is at that b k square. Please understand h naught over b L1 plus I L2 plus alpha okay, where h equals h naught ei omega t, alpha equals alpha naught ei omega t. Okay. That means in my motion I represent them as harmonic and I am writing my lift expression, but please understand it is a complex number. Okay. L1 I L2 L3 I L4. Similarly, my moment expression is given as minus 4 rho infinity u infinity square, sorry, this is also square, I am sorry about that, 4 rho infinity u infinity square b square k square h naught over b plus alpha naught into m3 plus I m4 e power I omega t. Okay. Now that reference gives you all these integrals. Okay. All these L1, L2, M1, M complete. Okay. This is an unsteady supersonic flow and they do a flutter analysis also, but flutter analysis part we will do later. I am just giving this reference gives the complete details of this. Now you know in supersonics you can get the lift and moment in this, but of course you need to know that integral, that is the key. Okay. Now can we make a approximation? Okay. Basically the pressure expression, because you know that this integral you need to know. Of course this is available, that is what I am saying. This integral is available and it is given in this form. Please understand, even in subsonic, okay, it's a similar form, even in subsonic flow. Okay. But this paper has taken even a trailing edge surface. Okay. So this is not just an aerofoil alone, it has taken a trailing edge also. The trailing edge can have its own motion. Okay. And then they have added one more, L5, L6, M5, M6. Okay. And this is the complete unsteady aerodynamic load. The next part is how do you do the flutter. That I thought we will first finish all the theory and then learn how to do the flutter analysis. Even in the calculation, that how do you get the lift expression. Okay. But the key points are, it is a complex number. Number one, the complex number essentially represents, complex number means what? It has a magnitude, it has a phase. Because you can write the entire thing as some constant, some magnitude into e power some I phi, some other Ri, some phase angle. Motion is at omega t, you will have a lift is having a phase difference between the motion. That is why lift will actually be a little slower depending on how the phase comes out to be. Okay. It is like you can write alpha and h, you say my lift is some L bar e power I omega t. Okay. Similarly my moment. This depends on, what is it? Okay. and this phase difference is the one which causes, actually it will lead to the flutter when it is aiding, because you know in resonance in any of the if you have studied the simple single degree of freedom system, when you have resonance you call it what? When you say your input, you always study the output, okay? And whenever the damping, actually your input value balances the damping force, you will find the resonance will come, okay? That's what you will have, that 90-degree phase shift will always be shown. When you draw the magnitude and the phase, you will find the phase curve will go like this. At resonance, the phase is 90 degree. Okay. This is similar to that because of there is a delay in the motion of the fluid which is going around the aerofoil. If the aerofoil is executing harmonic motion, the lift will not be at the same phase. It will have a different phase depending on your omega. Okay. That is what you basically capture, because if you assume quasi, immediately like what we said, every instantaneous angle of attack you take it, you find out the lift. Then there is no phase difference between motion and lift. Whereas if you include the unsteady aerodynamic theory, then you have a phase difference between motion and lift. That is like a input output, like a control system. Because later the control theory into this to see how we have modeled the unsteady aerodynamics in the subsonic case. Input is motion of the airfoil, output is lift. Now this is like a control system, okay, and you can always find a phase difference, okay, and that phase gives the essentially responsible for all your flutter various types of problems. That is why the flutter analysis itself is done using this theory. You can do flutter analysis like what I did earlier, that is you assume that it is a, there is no phase difference, very simplistic formulation I have assumed. Lift is every instant whatever is the angle of attack, that is proportional. Okay. If I use that, you will get, still you will do, but that is a very conservative analysis. This is more sophisticated approach to solving the unsteady aerodynamics problem. Now let us see, this is without making any assumption on the omega. Suppose if we make low frequency approximation, that is one end. Other end is I am making high frequency approximation. Okay. These are the two approximations I will make, and I will get a very simple closed form expression for pressure. Very simple, and then which I directly go ahead and then start using for my unsteady aerodynamics. I will not get into this, but of course this is there in this reference. That's why I wrote down, because you can download it from the internet, this paper. Okay. Now let us take the two simplistic cases. Okay. I am erasing this part. Okay. What was our, let us write the expression for the mu square, and from there we will do the low frequency, high frequency approximation. Okay. Because we wrote mu square is m square minus 1 p plus I m omega over a infinity m square minus 1 whole square plus let us say I want to do low frequency approximation. Okay. That means my aerofoil omega is very small. Now when I make very small, I am going to throw this term. Okay. Then my mu square, I am approximating m square minus 1 into p plus I m omega over a infinity m square minus 1. That's all. I am writing only this, because I am not neglecting this, because if you throw everything out, then you will not get an answer. Okay, I am only throwing this term out. Now if I write my Laplace inverse, because I have simplified this mu square, therefore my this is minus, as usual this is what we wrote, w bar a Laplace inverse of 1 over mu now Laplace inverse of 1 over mu is very simple, because this is nothing but p plus a whole square, so it is just an exponential term. So you will write your answer as, I am writing directly the answer, 1 by root of m square minus 1 0 to x w bar a psi e power minus I m omega over a in infinity m square minus 1 into x minus psi d. That's all. This is my 0 plus comma x. Okay. You see the difference between this integral and this. Okay. Only thing is I have a that j naught, which is a Bessel function. Here I don't have that, and this is very easy to integrate. Okay. What we will do is, let us find out the solution. Now pressure P bar upper is nothing but minus rho infinity I omega P bar plus u infinity delta P bar by delta x at z equals 0 plus. Okay. Then we will subtract this, we will multiply by 2, you will get a upper minus lower pressure. If I substitute this expression here, delta phi by delta x, you will find that quite a few terms will cancel out. Okay. This is going to be a very long exercise, because it's not, maybe it will take the entire board. Okay. I am just writing expression for you to, that is, I am substituting phi bar here. Okay. I will have, maybe I will write here, it will, so that I can go full, then we will erase that part. Okay. That is P bar minus rho infinity I omega phi bar is here. So you substitute minus I omega over square root of m square minus 1 integral this whole expression 0 to x e power I sorry, that W bar A psi e power minus I m omega over A infinity m square minus 1 x minus psi d psi. This is the first term, plus u infinity into delta phi by delta x. Okay. You have one x term, e power minus I m omega A infinity x. That is independent of this integration. Okay. So you can take it outside, you can differentiate it. Another one is 0 to x. That x is the upper limit, again that differentiation. So 0 to x, you will get the integrand itself. Okay. So you will have two terms, one with the integration, another one just the integrand. So you will, I will write the full expression, I m omega over A infinity m square minus 1 over root of m square minus 1 e power minus I, because I have first differential with respect to x. Okay. I m omega x over A infinity m square minus 1 integral 0 to x into e power I m omega psi over A infinity m square minus 1 d psi. This is, I have differentiated only this term. Okay. Then in the next one I keep it as it is, and that will be the same integral. So I will get minus 1 by square root of m square minus 1 e to the power minus I m omega x over A infinity m square minus 1. That is this term is kept outside. What is left inside is this term, which is an integrand, 0 to x integral and then differential with this expression only. So you will be left with basically W bar A x e to the power I m omega x over A infinity m square minus 1. Okay. This is okay. Now you see this term, you will find this will cancel with this. Okay. You will have W bar A x over root of m infinity square minus 1 into u infinity. These two terms this can go inside, you will get similar. You can have a omega and a omega sitting there. Okay. Now you, what we made was, it is a low frequency approximation. Okay. Let me write that final expression, then you will see how it will become highly simplified. That is, p bar u is minus rho infinity integral 0 to x W bar A psi e power minus I m omega into x minus psi over A infinity square, sorry, A infinity m square minus 1 d psi I omega over root of m square minus 1 into m square over m square minus 1 minus 1. This is the first two terms, and the next term will be minus w bar a x u infinity over root of m square minus 1. That's all. Okay. Now here only you make that, that's why this is a messy algebra. Okay. But final expression is going to be highly simplified expression, because now I make low frequency approximation. That means my omega here, I am setting it to 0. I said it is very small in comparison with this term. Okay. I will write another expression like this. Okay. I erase this part fully and write a very simplistic answer. Okay. This term will be highly simplified. P bar upper is, because I have substituted everything here, and I have got P bar upper is minus rho infinity, and this minus rho infinity, minus and minus, it's going to be plus rho infinity u infinity over m square minus 1 w bar a x. That's all. This is pressure upper, means this is pressure on the upper surface, Z plus. Okay. Pressure lower, you will have a minus sign, minus rho infinity u infinity over root of m square minus 1 w bar a. This is Z plus, this is Z minus. Okay. Now P upper minus P lower, it will be 2 times this. Okay. Now W bar A is nothing but the velocity of the fluid on the aerofoil where it is kept. So you can write that. Now I will write that expression. Okay. Because this is a very highly simplified form. Okay. Let us write P lower minus P upper. Okay. You will have a e power I omega t, it will come. That will be actually P lower minus upper means this minus that, so you will have 2 minus 2 rho infinity u infinity over square root of m square minus 1 w a e I omega t. That is, sorry, w a, we wrote it as w bar a e I omega t, right? So I have to put e I omega t multiply, then I will get pressure. This will be W a, velocity of the fluid on the aerofoil. Now we have to take, as usual, our reference. That is, this point is coming down with h, and this angle is alpha, and this is the leading edge. You have x naught, and this is any x. Okay. This is B, and this is B. Okay. Because this is my Z and this is my X. Okay. Now what is my WA? Because if you look at your motion, WA is written this. This is given if you look at the aerofoil thing. Go back to your notes, you will see WA is W bar A E I omega T, which is okay. Delta ZA, this is the aerofoil, the Z displacement of the aerofoil. This is what your, if you look back, your boundary condition. Okay. Now, what is Z bar? Z bar A, ZA, sorry, ZA is the displacement of the surface, because this is a thin line. Now I am taking a line, straight line. So, my ZA, because whether it is upper surface, lower surface, it is the same thing, because this is the line. This will be minus H minus X minus X naught alpha. This is my ZA, right? Now, what is WA? Now I have to substitute this back here. Okay. If I have to substitute this is delta ZA over delta T, means my WA becomes, maybe I write it here. Okay. My WA becomes delta ZA by delta T. This is minus H dot minus X minus X naught alpha dot, and then U infinity delta ZA by delta X. Delta ZA by delta X means this is nothing but alpha. So I will have okay. Now pressure upper minus pressure lower is what? You just substitute here. Okay. Now I have my pressure difference, I can get the lift, I can get the moment, okay, in closed form. This is the low frequency approximation. You will get 2B, this X anyway is a running variable, X minus X naught, because X naught is a constant. So you can, okay, start. So now you have the expression for the pressure difference. You can get lift as defined by earlier expression, and the moment also by the earlier expression. Okay. If you want, I can again write it for your for your convenience, because that will become simpler for you. Because so okay, let it be here. I write it here. Okay, your lift is integral P lower minus upper into 0 to 2B. Okay, 0 to 2B. And the moment, you can write it integral again 0 to 2B P, because no sub moment we are taking it as positive. Okay. So P upper minus P lower into X minus X naught into dx. Okay. This is my moment expression. What you have to do, you just have to take this expression, substitute there. Now you see the pressure on the aerofoil is a highly simplified form, highly simplified. just the rho infinity u infinity over m infinity under root. Okay. Now let us, then there is another approximation which is, sorry, let me, this is called the low frequency approximation. Now there is one more approximation which is called the high frequency approximation, and that is this clear? Because I will erase this part. That will also give you a closed form expression with a little difference. Okay, you will see this expression and there it will be little different. This expression will be different. That's all. That high frequency what is done is, in the high frequency expression, this term m square is actually, what you do is you take it inside, you write mu square, this particular term, you expand the whole thing, p square, this will be p square plus 2p into this plus this term, right? You multiply this inside. This m square minus 1 will cancel with some of the terms, but it will also have m square minus 1 p square. You say it is a high frequency because it's a large value, whether it is a m square minus 1 or m square, it doesn't make much difference. It's not a high Mach number. I am using p as the reference because it's going to be a very high frequency. So I am approximating it, please understand, m square p square plus m over this term, because 2 times, minus omega square over a infinity square, which is written as I omega, sorry, p m plus I omega over a infinity square. This is the approximation I make. You look back your original mu square expression, okay? In that, make this. Now this is very simple, mu square. Then mu is Pm plus I omega over a infinity. Then again I erase this part, okay? So your p bar 0 plus comma x becomes w bar a, right, Laplace inverse of this, okay, because Laplace inverse of 1 over mu, that is the same thing with the term. You will have e power I omega x minus xi over a infinity m, okay, because this is Pm. Now with a, sorry, minus sign, this is the, okay, this is again you substitute in the p bar upper, which is minus rho infinity I omega p bar plus u infinity delta phi over delta x, this p bar, and this is equal to 0 plus, because this is p upper. When you do that, this will become again much simplified expression, I'll just write that minus rho infinity I omega this will be minus I omega integral 0 to x w bar a psi 1 over m e power, sorry, there is a 1 over m divided by some m is there, sorry, 1 over m is there. Laplace inverse get 1 over m denominator, okay. E power minus I omega x minus psi over a infinity m d. This is the first term. Then u infinity delta phi by delta x. Okay. Again, this has two terms. Okay. So you will get, again you will have two expressions. Okay. It will become with I omega, because first you differentiate with respect to this. You will have a infinity m e power minus I omega x over a infinity m. Let me erase this part. Okay. Because this is going to be a long integral. 0 to x 1 over m e power I omega psi over a infinity m d psi minus w bar a x over m. Okay. Here you will find these two terms will cancel out. Okay. And you will be left with very simple expression where Pu is rho infinity a infinity okay, because u infinity over m is nothing but a infinity. So this is your expression for the pressure. Up, similarly, the lower surface P bar L, you will get minus rho infinity a infinity w bar a x. So you see, high frequency, low frequency, only difference is the term corresponding to this. Okay, because you will find that these two terms will cancel out. Okay. Because you will see what is the, no, there is one W, right? Here I must put a, there should be a, there is a W, because this term is there, W bar A. Because you will have I omega, because A infinity m is what? This is nothing but u infinity. U infinity will cancel out. Then this term will go inside. This term is nothing but this term. Okay. So this is same as this. This is with a minus sign. This is with a plus sign. So you will find these two identically get cancelled. Okay. Leaving behind only this term, and this will have u infinity over m with a minus sign, which is basically a infinity, and that minus and minus with the rho it will become. So this becomes your just a high frequency approximation. Okay. This is nothing but density at infinity, speed of sound at infinity. This is nothing but the velocity at the point where you are having WA. And this theory is called piston theory. Okay. And this is what is used in supersonic panel flutter calculation, everything. Okay. So that is called the piston theory. Okay, I erase this part and I'll just briefly describe why it is called piston theory. Okay. So you had two approximations. One is the high frequency approximation, another one is the low frequency approximation. This is high frequency. Low frequency you had, what was that expression? So if you write the low frequency and high frequency, you will see this is the low frequency. You will have P bar U is this is the high frequency. So you see the difference. Only thing is, instead of U infinity over, now you may say, well, if the Mach number is very large, this is nothing but what? This one you cancel out, you will get speed of sound, then that, sorry, U infinity over A infinity, U infinity will cancel out, you will go to A infinity. That is what the piston theory is. Okay, but our theory is valid up to Mach number 2, 3. So that is why one is the low frequency approximation, another one is called the high frequency approximation. So we essentially have now in supersonic theory a closed form expression for pressure on the airfoil. Only thing is we have to define what is my WA. WA is, you know that is delta G over delta T plus U infinity delta G by delta X. Because WA is the velocity of the fluid on the aerofoil. Motion of the aerofoil is given by ZA. Please understand. That's why you should not confuse with that. Because you remember we wrote WA is delta T, U infinity, delta X at Z equal to 0 plus minus. This is flow velocity, this is the body velocity. Now you know the body motion. Flow velocity is equal, so you simply substitute body motion into this. That means you have your pressure in terms of the body motion. And then you can solve your equation. That means my load is known, then I can use essentially what is the external force. External force is now a function of the body motion. Okay, please understand. But this is not a complex number here. You know, here what happens is this directly you are giving only the factor and the motion. Okay, you understand, h dot alpha dot, you directly put it there. Use the exact no approximation for omega, then you will start having the complex number. So basically you will solve for flutter problem complex eigenvalue theory. Actually complex eigenvalue problem you have to solve, but that we will learn at the later part. Okay. Now I thought I will briefly mention, this is for two-dimensional structure. Okay. And you know you can always write the equation of the surface based on our geometry. What is the motion? And you can immediately 0 plus 0 minus is only because you know thickness is not generating any lift. So you will have the mean line only. Mean line you can, and you can immediately write your load. Now this theory is very simple. Even if you have a panel like a supersonic flight the panels, the panel will vibrate. And the piston theory essentially means each small area is considered as though it is a piston. It's a long piston. And you just move whatever is the pressure there, that is the pressure given by that expression. That is why it is called the piston theory. Okay? Very approximation, because you can do, I have that derivation. Maybe I'll just briefly mention to you why it is called the piston theory. Okay? I'll just briefly do very simplistic problem. Suppose you have a this is the highly simplified. You have a very long piston, you say, you assume. And here there is no flow, it is a stationary. You put a piston here. Okay. The piston is given a velocity, say u0. What is the pressure that acts on the piston? Okay. So you see, this is a long tube. I move the piston with the velocity. What is the pressure that acts on this piston? That is what our problem. Once I have the pressure, then that is exactly equal to that. Then I will know. This is a one-dimensional disturbance problem. So potential flow one-dimensional is okay. One-dimensional problem with boundary condition delta phi over delta x is u naught at x equals to 0 for t greater than 0, because x is 0 is this part. Now for this the solution, this is the wave equation. Okay, you can always write solution as phi as f of x minus a infinity t, but I will take only the a minus a infinity t because this is the wave which is propagating on the right side. Okay, because you can have wave propagating on this side, wave propagating on this side. This is the wave which is propagating on the right side, because if you have a wave, something happens at t equal to 0. This wave moves at t equal to some delta t. It has moved here like this. Okay. That means this equation is what? Because you are only shifting because the wave moves with the velocity a infinity delta t. So my x-axis gets simply shifted. Okay. This is the right traveling wave. Left traveling wave, you put a plus sign. Okay. That is why you use this solution only for this problem with the piston moving, because you don't take the other solution. Okay. So when you have this is the solution, you can find out what is your pressure, because you know that delta phi over delta x is nothing but delta f over delta x, which is u naught. Okay. And the pressure on the piston, what is that? P minus P infinity. This is given as minus rho infinity. What was that? Delta phi over right? Huh? But this is 0 because u infinity is 0, because it is a stationary fluid. So this will be what? Minus rho infinity delta phi by delta t. Delta phi by delta t will be delta phi over this term into, you can write it as delta phi over delta x minus a infinity t, because this is one one term into delta of x minus a over delta t, which is nothing but this is what? Delta phi by delta x, that is u naught. This is u naught. Okay, this is minus a infinity. So you will have plus. So rho infinity, a infinity, u 0. Okay. Okay. Now you see what is W naught. W naught is velocity of the piston at the left end. WA is what? There is nothing but the fluid velocity, which is basically you have to write it as the piston velocity, because WA is given by what? You know that delta ZA over delta T plus u infinity delta Z. Okay. This is the body motion. So essentially the velocity of the body at that point. So this is the piston theory. Okay. That is why in supersonic flow, on the surface, if you consider, every small region acts like a independent piston with its own long cylindrical, like if this is kept up like this, because in the aerofoil if you take it like this is like a long cylinder. You find out whatever is the velocity there, you put it there. So each is a cylindrical, long infinite cylinder. So this is the piston theory, but high frequency. Okay, low frequency is a little different.